everyone, thank you so much for clicking onto the video. Today's learning objectives are to firstly explain why chemists aim to design processes that do not require a solvent and that use non-hazardous starting materials, to explain why chemists aim to design production methods with fewer steps that have a high percentage atom economy, and use reactions in the specification to devise a synthesis with up to 4 steps for an organic compound. So now we're going to look at organic synthesis. The synthesis of an organic compound can involve several steps, and these are factors that chemists aim for when planning synthetic routes. So synthetic routes are just routes that we can take to get from one organic compound to another. So for example, we could make an amine from an alkene. So the first factor we have to look at is using non-hazardous starting materials and processes that don't require solvents. And this is because solvents are often flammable and they're also toxic, and so we get some safety risks. And the second point is that if the solvent has to be disposed of after the reaction is complete, then we'll have a lot of waste which will be produced. The reason we want to use non-hazardous starter materials is that we want to limit the potential for accidents and environmental damage. The second factor we need to take into consideration are reactions that have a higher atom economy. And so chemists are also concerned with designing processes that aren't too wasteful. And if a reaction has a high atom economy, then we get less waste because more of the reactants will form the products. So processes with high atom economy and high percentage yields are preferred because they convert more of the starting material into useful products. And so we get less byproducts, and so we get less waste. And the last thing is that we want to have synthetic routes that have fewer steps. And this is because waste can also be reduced by designing synthesis routes that have as few steps as possible. And this makes sense because if you have a think about a really, really long synthesis that has lots and lots of steps, that means we get lots and lots of byproducts that we won't actually use and they won't be useful for us. So that will be waste compared to if we have a fewer steps, then we have fewer byproducts, and so we have less waste. So now we're going to look at the relationships between functional groups. So this is basically a mind map of how to get between different functional groups. And you should probably have this memorized in your head because it'll make it a lot easier to think of reaction schemes. So I'm first going to start off with the alkane. And we're firstly going to produce a halogenoalkane or a haloalkane from this alkane. And there's only one reaction that will make a haloalkane from an alkane, and that's free radical substitution. And that's where we have a halogen and also UV light, and we can add the halogen to the alkane to form this haloalkane. And we can also reverse this, and so this is why this arrow goes 2 ways. And now looking at a halogenoalkane or a haloalkane to an alkene, this is our elimination reaction, where we use some hot ethanolic OH minus to eliminate the bromine to form a double bond. And so that's how we get the alkene. So I'm actually going to put those in different colours. So for the free radical substitution, we need a halogen. And really important is that we need UV. And for this elimination, we need hot ethanolic sodium hydroxide. And then to get from a haloalkane to a nitrile, this is a nucleophilic substitution reaction. Because we're substituting the halogen with a CN. And so what we need is a CN minus ion. So how we get that is we add potassium cyanide followed by some acid. And then the next reaction is from this haloalkane to this amine. So this is again a nucleophilic substitution. And this is where we used ammonia as the nucleophile. And that was also our reagent. And now we're going to look at an alkene to an alcohol. So this reaction is a hydration reaction. And we have to add some water. And we would also need the presence of a strong H+ catalyst. So we would need an acid catalyst. And now we need to look at the haloalkane to an alcohol. So we missed that out before, but this is also a nucleophilic substitution reaction. But this time we're using an OH- as the nucleophile. And so the reagent we need is something like sodium hydroxide. But this time, instead of it being hot and ethanolic, like when we had the elimination reaction, we need it to be dissolved in water. So we need it to be aqueous and also cold. So we have cold, aqueous, sodium hydroxide or potassium hydroxide. And so what we can do to get from an amide to a nitrile is dehydrate it. So this could be our dehydration reaction. So this is if we have the arrow going this way. And this free radical substitution is actually just from an alkane to a haloalkane. And the elimination reaction is from the haloalkane to the alkene. And so we have a dehydration reaction to go from the amide to a nitrile. And what we need is we need some phosphorus oxide. So we need to heat it with phosphorus oxide. And then to go from a nitrile to an amine, this is a reduction reaction. So we have a reduction reaction here. And this is our reduction that we looked at with the hydrogen and nickel catalyst. And to get from a nitrile to a carboxylic acid, this is a hydrolysis reaction. So here we have hydrolysis. And we need some water and also a H+ catalyst. So we need water and some kind of acid. And then this reaction here to get from acid chloride or an acid anhydride to an amide. So all of these acid chloride and acid anhydride reactions are all acylation reactions because these are both acid derivatives. So here we have an acylation reaction. And the nucleophile we use to form an amide is ammonia. So that is our reagent. And we can actually call these acylation reactions nucleophilic addition-elimination reactions as well. And it's the same thing. So we have nucleophilic addition, elimination. And so this is also an acylation reaction. But this time our reagent is water. And then to form an ester, we also have an acylation reaction. But this time our reagent is a primary alcohol. And now we only have a few more, and these ones are the ones which are a bit more simple. So first I'm going to look at the alcohol, aldehyde, carboxylic acid and ketone. So to get from an alcohol to a ketone, what we need to do is oxidize it. And we need to remember that only secondary alcohols will oxidize to ketones. And how we do that is using potassium dichromate and a H+ ion, so a H+ catalyst. So if we're going this way, then we have oxidation. And if we're going this way, we have reduction. And so for reduction, what we use is sodium borotetrahydride, or LiAlH4. And for oxidation, what we use is potassium dichromate with a H+ catalyst. And this is the same for an alcohol to an aldehyde and a carboxylic acid. So primary alcohols will oxidize to an aldehyde and the aldehyde will oxidize to a carboxylic acid. So going this way, we have oxidation, and here we have oxidation as well. And these are both using potassium dichromate with a H+ catalyst. So if we go in the other direction, so from an aldehyde to an alcohol, we have the same thing. So we have a reduction reaction here. So we use sodium borohydride or lithium aluminium tetrahydride. And we have to remember that we can only oxidize an aldehyde to a carboxylic acid and we can't go the other way. We can also go straight from a primary alcohol to a carboxylic acid. So this would be an oxidation reaction. And we would use the potassium dichromate with a H+ catalyst. And then to get from a carboxylic acid to an ester, this is an esterification reaction. If we went the other way, it would be a hydrolysis reaction. And for esterification, we need an alcohol. And for hydrolysis of an ester, we need a H+ catalyst and also some water. And then to get from an ester to an alcohol, again, this is an esterification reaction. If we go from right to left and from left to right, this is a hydrolysis reaction. And so again, with the esterification, this time we need an acid, so we need a carboxylic acid or an acid derivative. And then for hydrolysis, we need water and H+ catalyst. And we also need to know the relationships between aromatic compounds. So I'm going to start off with drawing benzene in the middle, because from benzene we can form different aromatic compounds. So we have benzene. And the first reaction that I can think of is the nitration of benzene. So this will form a nitrobenzene. And so I'm going to draw it over here. So it's just a benzene with a nitro group attached. So this is our nitrobenzene. And from this nitrobenzene, we know that we can form an amine because we can reduce it. So I'm going to draw it down here. So instead of the nitro group now, we have an NH2 group. So this is phenylamine because an amine takes priority, and so it becomes the root of the name. Another thing that we can form from benzene is we can go through acylation. So that's when we can form an acyl substituted benzene. So I'm going to draw it over here. So we have a benzene, and now we have a C double bond O and then an R group attached. So we have an acyl group now attached to the benzene. So this would be called something like 1-phenyl because the acyl bit takes priority. And then we would have ... depending on what the R group was. So for example, if we had R is equal to CH3, then the name would be 1-phenyl ethanone. And so we can also call this an aromatic ketone, so a ketone with a benzene group on it. And so now we can put in some arrows to just look at all the different reactions. So to get from benzene to nitrobenzene, what we need to do is we need to nitrate it. So this is a nitration reaction. And what we need to use is concentrated nitric acid and also concentrated sulfuric acid. And sulfuric acid is the catalyst. And to get from nitrobenzene to phenylamine, this is a reduction reaction. And instead of having what we normally use to reduce, for example, an aldehyde to a primary alcohol, so the sodium borohydride or the lithium tetrahydroaluminate, for this particular reduction reaction, we have to use hydrochloric acid and a tin catalyst. So it's only the reduction of nitrobenzenes that we use this reagent and this catalyst. And now finally the reaction to form this aromatic ketone or this acyl substituted benzene. This is an acylation reaction. So what we need is we either need an acyl chloride and an aluminium chloride catalyst. And so if you remember back to when we were looking at the acylation of benzene, this is actually an electrophilic substitution reaction. And so we need the aluminium chloride catalyst to form the electrophile. So instead of using acyl chloride, we can also use an acid anhydride. So it's really important that you know all of these reactions as well as all the reactions for non-aromatic compounds, because it'll help you in thinking of ways in which we can produce different organic compounds. Now we're going to have a look at reagents used in organic chemistry. So firstly, we're going to look at oxidizing agents, and the oxidizing agent that we've looked at is potassium dichromate. So this is our K2Cr2O7, and this has to be acidified with a dilute sulfuric acid in order to oxidize alcohols. So what we can do with this potassium dichromate is oxidize primary alcohols to aldehydes and then eventually to carboxylic acids, or we can go straight from a primary alcohol to a carboxylic acid. And we also need to know that secondary alcohols are only oxidized to ketones. And then for reducing agents, we need to know that different reducing reagents have different capabilities. And that's why we've looked at 3 different reducing agents. So the first is sodium tetrahydride borate, or we can also call it sodium borotetrahydride. And actually an alternative to this NaBH4 is actually LiAlH4. So either of these can be used, and it can be used in aqueous solution. And these reducing agents will reduce polar unsaturated groups, such as C double bond O, because we have the carbon, which is a partially positive atom, and then we have the oxygen, which will be partially negative. And this is because the oxygen is much more electronegative than the carbon. However, these reducing agents won't be able to reduce non-polar bonds, so such as the carbon-carbon double bond. And this is because it generates the nucleophile H-, which can only attack this carbon with a partially positive charge, but it's repelled by the electron-rich carbon-carbon double bond because we know that the double bond is an area of high electron density. The second reducing agent we have is hydrogen with a nickel catalyst. And this is what we use to reduce carbon-carbon double bonds, but not carbon-oxygen double bonds. And this is actually also used to reduce nitriles. So to get from a nitrile to an amine, we could use hydrogen with a nickel catalyst. And then the third reducing agent we need to know about is tin and hydrochloric acid. So this is used to reduce an RNO2 group to an RNH2. So for example, we could have a nitrobenzene and we would reduce this to a phenylamine. And then finally, we need to know about dehydrating agents. So alcohols can be converted to alkenes by passing their vapors over heated aluminium oxide or by acid-catalyzed elimination reactions. So now we're going to look at how to work out a reaction scheme. So first of all, we start by writing down the formulas of the starting molecule and the target molecule. So we can see in the diagram that we have our starting material labelled A and our target material labelled X. And then the next step is to write down all the compounds which can be made from A. So these are B, C, D, and E, and all the ways in which X can be prepared. So we've got T, U, V, and W. And it's really important to keep the number of steps as small as possible, and this is to maximize the yield of the target. Sometimes you'll be able to see straight away that a particular reaction will be needed. So for example, if the target molecule has one more carbon atom than the starting material, then it's really likely that the reaction of cyanide ions with a haloalkane will be needed at some stage, as this is the only reaction we have where we can increase the length of the carbon chain by 1. So the example we're going to look at is the synthesis of propanoic acid from 1-bromopropane. So first, I'm just going to have a think about some reactions that I can have. So I'm going to start off with 1-bromopropane. So this is a primary haloalkane. So I'm just going to write that I have a primary haloalkane. And one of the reactions which comes to mind with primary haloalkanes, or haloalkanes in general, is nucleophilic substitution. And things that can act as nucleophiles are either negative ions or species that have that lone pair of electrons that can be donated to form a covalent bond. And so we can react primary haloalkanes with hydroxide ions, for example, to form an alcohol. So I can form a primary alcohol from this primary haloalkane. And this is by adding aqueous OH- ions. The second thing I can do is also a nucleophilic substitution reaction. So this time I can add cyanide ions. So if I add some cyanide ions, then I get a nitrile, and I have a primary nitrile, because this Cn- would replace the bromine. And then thirdly, I can also use ammonia as a nucleophile. So if I add ammonia, then I can form a primary amine. Because if you remember the nucleophilic substitution with ammonia, we have a second ammonia nucleophile that comes and attacks. And so we remove one of the hydrogens off the NH3 to form an amine, which is NH2. And then the final thing that we can do with haloalkanes is we can go through an elimination reaction where we have the OH- this time heated and dissolved in ethanol. So we have alcoholic OH-, and this would be to form an alkene, because we're basically adding a double bond and getting rid of the bromine. So these are the two reactions that can happen with haloalkanes. We can either get nucleophilic substitution, or we can get elimination. And so here we have our nucleophilic substitution. And this one is our elimination reaction. And now I'm going to do the same thing, but with the target molecule. So what we can make the target material out of. So this time I'll start with the material on the right. So we have the end thing that we want to get, which is our propanoic acid. So we have a primary carboxylic acid, and ways in which we can form this primary carboxylic acid is, firstly, we can undergo oxidation. So we can form it from either a primary alcohol or an aldehyde, because we know that primary alcohol will oxidize to an aldehyde, and an aldehyde will then oxidize to a primary carboxylic acid. So we have, we can get this from an aldehyde, and this would be using the potassium dichromate with a H+ catalyst, or we could also get this primary carboxylic acid straight from the primary alcohol. And so again, this would be using our potassium dichromate. We could also get this primary carboxylic acid from a nitrile. So we could have a primary nitrile, and we would achieve this by adding some water with a H+ catalyst. So that's a hydrolysis reaction. And we could also get a primary carboxylic acid by using an acid derivative. For example, we could have an acid anhydride or an acyl chloride. And the way we would convert an acid derivative to carboxylic acid would be adding some water. And we actually also use some H+ as a catalyst. So now we can label our reactions. So these first two are oxidation reactions. And then this third one is a hydrolysis reaction. And this last one is an acylation reaction. So the nucleophile we're using is water. And now we can start to see what our reaction mechanism would be. So this is what we end up with. And now what we do is we can cross off all the things which aren't the same. And so basically what we need to do is we need to find something that is in common with both of these intermediates. So we can see that we've got this primary alcohol here, and we've also got a primary alcohol here. So this could be a possible intermediate. Or we have a primary nitrile here and also a primary nitrile here. So this could also be an intermediate. And there's nothing else in common, and so all of these four can't be used. So we don't do these. And so we're left with either a primary haloalkane going to a primary alcohol going to a carboxylic acid, or a primary haloalkane going to a primary nitrile and going to a primary carboxylic acid. So now we need to decide between the two of them. And how we do that is, I'm just going to write out the different molecules, and we should begin to see why we can't use one of these methods. So we're going to start off with our primary haloalkane. So we have 1 bromopropane, which is CH3, CH2, CH2, Br. This is our 1 bromopropane. And so we've said that this can either form or our primary nitrile. So our primary alcohol would be propanol, or propan-1-ol, sorry. And this is because we've used the OH minus as our nucleophile. And so we would have aqueous NaOH as the reagent. And then the primary nitrile that we would produce would be CH3, CH2, CH2, and then CN. So this is butane nitrile, because we have 4 carbons. And what we've done here is we've added some CN minus. So what we do is we add potassium cyanide followed by some H+. So now if we have a look at the other side, which is propanoic acid, which is our target molecule. So we have CH3, CH2, and then COOH. So this is propanoic acid. And we said that we could form this either from a primary nitrile or a primary alcohol. So the primary alcohol would be propan-1-ol. So we'd have CH3, CH2, and then CH2OH. So this would be our first one. And how we would produce propanoic acid from propan-1-ol. We actually need to label this one as well. Is that we would add potassium dichromate with a H+ catalyst because we're oxidizing it. So that would also be reflux. And the other way was using the primary nitrile. So we would have propane nitrile. So CH3, CH2, and then C triple bond N. And we could form this by a hydrolysis reaction, so adding water and a H+ catalyst. So this is our propane nitrile. So now we can see why we can eliminate one of these methods. And it's because here we have butane nitrile, but here we have propane nitrile. So they're not the same. And so we can't go through this method to get from 1-bromopropane to propanoic acid. And so we have to use propan-1-ol as the intermediate. So we've now found our reaction scheme. So what we have is that for step 1, we have 1-bromopropane, so CH3, CH2, CH2, Br, and this will form our CH3, CH2, CH2OH, which is our propan-1-ol. And this is 1-bromopropane. And what we've done there is we've added cold aqueous sodium hydroxide. So we always write down the reagent and not the nucleophile. So we don't write OH minus, we write NaOH, which is the reagent. And then step 2 is propan-1-ol. So CH3, CH2, CH2OH. And this will go on to form our propanoic acid. So CH3, CH2, C double bond O, and then OH. So this is propanoic acid. And the way we do that is using oxidation. So we add potassium dichromate and a H+ catalyst, and this is a reflux.